Unveiling the Beauty of Science, the Timeline of Matter and Atoms.
Hi everyone, I am Jamir and I am thrilled to take you on a journey through time, exploring the fascinating history of matter and atomic theory. We'll be traveling from ancient philosophical musings to the cutting edge discoveries of a modern science. Get ready to amaze. This presentation is my entry for my prestigious interschool science communication competition, and I'm excited to share my passion for the beauty and wonder of science with you all. For centuries, humans have pondered the fundamental building blocks of the universe. What is matter made of? Is there any smallest unit of matter? The answers to this question have shaped our understanding of the world, leading to the incredible technological advancements and revolutionizing various fields of science. In this video, we'll explore the key milestone in the development of atomic theory, highlighting the brilliance of scientific minds throughout history and the interconnectedness of their discoveries.
Atoms are the basic building blocks of all matter. They're extremely small, make up everything in our universe. Stars, these bananas, our entire body. All made of tiny atoms fit together differently. Atoms are made up of three particles called electrons, protons, and neutrons. Electrons are the smallest, their charge is negative, spinning really fast all around the nucleus. The protons, bonds, located in the center, forming the nucleus with neutrons that have no charge. And when particles amass different, makes various elements. One proton, one electron, the simplest atom's hydrogen. Every element has its own atomic number, tells us how many protons located in its center. Less protons means less mass, like hydrogen, that's a gas. It's less dense in the air, one proton in the nucleus. Because protons have a strong positive charge, push each other away, but pull back with a strong nuclear force. Balance makes atoms possible, everything in the universe. Different atoms clumped together are known as molecules.
Our journey begins in ancient Greece, where philosophers like Leucippus and Democritus first proposed the concept of the atom. Atomos meaning invisible. They imagined tiny indestructible particles that made up everything. However, their ideas were largely overshadowed by Aristotle's theory of four elements, which is earth, fire, water, and air. Fast forward to the 17th and 18th centuries, a period of significant advancement in chemistry. Robert Boyle challenged the four-element theory, defining elements based on their properties. Antoine Lavoisier established the law of conservation of mass, laying to the groundwork for modern chemistry. Then came John Dalton, who revived the atomic theory, proposing that elements are made of tiny, invisible atoms. All atoms of an element are identical, and atoms combined in a simple whole number ratios form compounds.
Each of them contributed to answering the eternal question, what is stuff made of? It was around 440 BCE that Democritus first proposed that everything in the world was made up of tiny particles surrounded by empty space. And he even speculated that they vary in size and shape depending on the substance they compose. He called these particles atomos, Greek for indivisible. His ideas were opposed by the more popular philosophers of his day. Aristotle, for instance, disagreed completely, stating instead that matter was made of four elements: earth, wind, water, and fire. And most later scientists followed suit. Atoms would remain all but forgotten until 1808, when a Quaker teacher named John Dalton sought to challenge Aristotelian theory. Whereas Democritus's atomism had been purely theoretical, Dalton showed that common substances always broke down into the same elements in the same proportions. He concluded that the various compounds were combinations of atoms of different elements, each of a particular size and mass, that could neither be created nor destroyed. Though he received many honors for his work, as a Quaker, Dalton lived modestly until the end of his days. Atomic theory was now accepted by the scientific community, but the next major advancement would not come until nearly a century later, with the physicist J.J. Thomson's 1897 discovery of the electron. In what we might call the chocolate chip cookie model of the atom, he showed atoms as uniformly packed spheres of positive matter, filled with negatively charged electrons. Thomson won a Nobel Prize in 1906 for his electron discovery, but his model of the atom didn't stick around long. This was because he happened to have some pretty smart students, including a certain Ernest Rutherford, who would become known as the father of the nuclear age. While studying the effects of X-rays on gases, Rutherford decided to investigate atoms more closely by shooting small, positively charged alpha particles at a sheet of gold foil. Under Thomson's model, the atom's thinly dispersed positive charge would not be enough to deflect the particles in any one place. The effect would have been like a bunch of tennis balls punching through a thin paper screen. But while most of the particles did pass through, some bounced right back, suggesting that the foil was more like a thick net with a very large mesh. Rutherford concluded that atoms consisted largely of empty space, with just a few electrons, while most of the mass was concentrated in the center, which he termed the nucleus. The alpha particles passed through the gaps, but bounced back from the dense, positively charged nucleus. But the atomic theory wasn't complete just yet. In 1913, another of Thomson's students by the name of Niels Bohr expanded on Rutherford's nuclear model. Drawing on earlier work by Max Planck and Albert Einstein, he stipulated that electrons orbit the nucleus at fixed energies and distances, able to jump from one level to another, but not to exist in the space between. Bohr's planetary model took center stage, but soon it too encountered some complications. Experiments had shown that rather than simply being discrete particles, electrons simultaneously behaved like waves, not being confined to a particular point in space. And in formulating his famous uncertainty principle, Werner Heisenberg showed it was impossible to determine both the exact position and speed of electrons as they moved around an atom. The idea that electrons cannot be pinpointed but exist within a range of possible locations gave rise to the current quantum model of the atom, a fascinating theory with a whole new set of complexities whose implications have yet to be fully grasped. Even though our understanding of atoms keeps changing, the basic fact of atoms remains. So let's celebrate the triumph of atomic theory with some fireworks. As electrons circling an atom shift between energy levels, they absorb or release energy in the form of specific wavelengths of light, resulting in all the marvelous colors we see. And we can imagine Democritus watching from somewhere, satisfied that over 2 millennia later, he turned out to have been right all along.
The 19th century witnessed a revolution in our understanding of atoms. Dalton's model, while groundbreaking, was incomplete. Dmitri Mendelev's periodic table organized the known elements based on their properties. Predicting the existence of undiscovered elements is a testament to the power of scientific organization.
Table is instantly recognizable. It's not just in every chemistry lab worldwide. It's found on t-shirts, coffee mugs, and shower curtains. But the periodic table isn't just another trendy icon. It's a massive slab of human genius, up there with the Taj Mahal, the Mona Lisa, and the ice cream sandwich. And the table's creator, Dmitri Mendeleev, is a bona fide Science Hall of Famer. But why? What's so great about him and his table? Is it because he made a comprehensive list of the known elements? Nah, you don't earn a spot in Science Valhalla just for making a list. Besides, Mendeleev was far from the first person to do that. Is it because Mendeleev arranged elements with similar properties together? Not really, that had already been done too. So what was Mendeleev's genius? Let's look at one of the first versions of the periodic table from around 1870. Here we see elements designated by their 2-letter symbols arranged in a table. Check out the entry at the third column, fifth row. There's a dash there.